So once upon a time, we think this area probably looked like this, right? Well, not this area, but this area plus the rest of the continent. So this is North America, as it probably looked around 500 million years ago. All right. These rocks were accumulating in this ocean basin at that point, right? This is a part of the Iapetus Ocean, predecessor to the Atlantic Ocean. All right, the Atlantic Ocean did not exist yet. It wasn't even a twinkle in Iapetus's eye. All right, it was way off in the future. What's the age of the oldest oceanic crust in the Atlantic? 180. Ooh, I should have saved the pencils. What's the age of the oldest oceanic crust?
180?
Yeah, around 180, 190, maybe as old as 200 million years old. All right, so the Atlantic is 200 million years old or younger. It's post-Pangea. The Iapetus Ocean is much older than that. It's pre-Pangea. The Iapetus Ocean used to separate the continents before Pangea got put together. You guys are geology majors, so you know this, right? You guys are not sort of at the same level as, say, an introductory geology student who might be coming into this thinking that geologic history begins with Pangea and plays out from there. All right? There's a lot that happened before Pangea got put together. So the story of the Billy Goat Trail is partly the story of putting Pangea together with a whiff wafting in from the west of Pangea breaking apart. Aaron, do you see any evidence of that nearby?
Wait, what was I down?
So there are blocks of rock around here that look different from the other ones.
Mm-hmm.
They in fact look a lot like the reddish rock that C&O Canal locks are made out of. All right? So that'll be part of our story too, but that's a rock that formed on the breakup of Pangea, whereas everything else we're talking about here is about Pangea getting put together. So, Iapetus Ocean. What kind of sediments were accumulating down there in the Iapetus Ocean between this volcanic island arc and North America? Greywacke sediments. And what were they being deposited by? Turbidites. Let me show you a picture of a turbidite, because I'm sure you've forgotten what a turbidite looks like. There, okay. Ta-da! All right. How do we know that these were deposited by turbidites? What's the evidence that suggests that? Graded beds. Do you want to see a graded bed?
Yes.
There's one.
Mm-hmm.
Everyone see how that's coarse grained at the bottom, and then it gets finer as you go up towards the top? Awesome, beautiful example of a graded bed. If I were writing a paper about the geology of the Billy Goat Trail, I'd probably want to put my sense of scale down next to this and take its portrait, because it's a real nice example of a graded bed. Questions? I'm going to put it down right here. It better still be here when we all leave. All right. Something else you'll observe around here looks kind of like this.
Mica schist.
What am I looking at here?
Mica schist.
Yeah, it's actually schist. You can see the individual grain, so it's not as fine grained as a phyllite. I would say it's a schist. All right, so some of this rock has been metamorphosed to schist grade. All right, it's basically developed nice big flakes of muscovite mica that are those silvery little mirrors that are shining the light of your eye. All right, those muscovite mica grains therefore are metamorphic mica, and if we date them, we date the time that those greywacke sediments got heated up and metamorphosed. Somebody remind me what that date is? 460, good. So potassium argon dating of the white mica, the muscovite mica here, suggests a crystallization age of 460, which means that's when these oceanic sediments stopped being oceanic sediments and started transitioning into the sorts of rocks we expect in the middle of a mountain belt. Notice how they're all lined up in the same direction? What's that called?
Foliation.
Foliation, right? So metamorphic foliation, go ahead, you be the volcanic islands, I'll be North America, develops when poor oceanic sediments or other rocks get caught between two colliding land masses. So when there's differential pressure applied to them, sigma 1 is this way, they have no choice but to grow in the sigma 2 and sigma 3 directions. There's also a lot of folding in these rocks. One example of that is right here. Unfortunately, it's not facing you guys, and I don't think I can move this boulder. There's a nice arch of a fold here. Did anyone see any folds as we walked along the path?
Yeah.
Good. Yeah, they're all over the place. So one of the things that we're going to want to measure as we break out our Brunton compasses and start assessing these rocks is we want to measure bedding if we can find it. We want to measure foliation if we can find it. We want to measure folds if we can find them. And we still have that question lurking in the back of our mind. Even though we haven't seen Mather Gorge yet, we're going to see Mather Gorge and we're going to wonder why the heck Mather Gorge is there. So we want to also test the joints alone can explain Mather Gorge hypothesis. So we want to collect some joint orientation data. And the good news is there's lots of joints in these rocks. They're highly fractured. Now, when you get turned loose to start measuring these rocks, I want you guys to make sure that you're only measuring rocks that are actually part of the bedrock. Because there are bedrock outcrops here, and then there are loose pieces of rock. And if you measure this joint face, that doesn't tell you a damn thing because this thing's not in place. All right? So, what do we call rocks like this? Float. Friends don't let friends map float. All right? Words to live by. So, if you see somebody measuring something you think, that might be float, then go ahead and, alert them to the fact that they might be screwing up the class's data. Did I just say the class's data?
Yeah.
What do I mean by that? Yeah, we're working as a group here, okay? You guys are collaborating. So rather than just Doug going and collecting 5,000 joint orientations on his own, right, and then writing his paper based on that, I think a better plan is that everybody collects all kinds of data in different areas, and then after the trip, you pool that data together. So suddenly you have access to not just your data, but 17 other people's data as well, and you've got a bigger data set, which means what?
More accurate.
Yeah, you're more likely to get the real picture of what's going on if you've got more data. All right? Okay, so what I think I'd like for us to do at this point is fan out in this area and spend about, I would like to say 10 minutes, but it'll probably take us more like 15 or 20 minutes to go and collect some measurements. All right? So we're going to break out our Brunton compasses. We're going to refresh our memory as to how to use those. If we don't remember how, then we're going to ask myself or we're going to ask Aaron, and we will help you get down some data. When you're writing this stuff down in your field notebook, you want to note down not only the strike and the dip or the trend and the plunge, but you want to note down what the heck it is that you're measuring. Are you measuring foliation? So you should write like fol, period, 134/68 or whatever, okay? So make sure with every set of numbers that you're writing down, you're also writing down what it is you're measuring. Good note keeping is key. Everyone's already written today's date, right, in their notebook. Billy Goat Trail, structural geology field trip, led by Callan Bentley, sort of partly cloudy day, Aaron Barth, assistant. Put down all sorts of details in there, even if they seem extraneous, because they will jog your memory later. So if you're in doubt about whether to put it in your field notebook, the answer is yes. All right, better to have it and not need it than need it and not have it. Okay, so 10 minutes ideally, and I'll give you up to 20. I want each person to come up with between 7 and 10 measurements. All right? 7 to 10 good orientation measurements of bedding, foliation, joints, or folds. Ready? Set? Go!